So I'm a postdoc researcher from University of Bologna, Italy, and here I will present a work in collaboration with ASU, Arizona State University. It's a digital twin to simulate microscale human thermal exposure and comfort in urban environments. And um, to be honest, I was mostly prepared for a really good introduction toward thermal comfort, but I I attended like more than 20 sessions on thermal comfort, so I decided now to just discuss more practically toward the subject, as I guess it's the last one in thermal comfort. Um, so just to have an add to today's keynotes on digital twin, um, more probably one would ask, oh, why we should choose digital twins instead of simulations. The response is, I mean, in thermal comfort that I experienced modeling and simulations. It takes more than 40 hours or even more for simulating um, simple urban space for MRT, UTCI, and like other thermal comfort um, factors like PET. So developing a digital twin that is going to work real time is a challenge for us, but it will bring us so many advantages. So because we can talk about real time managing for urban policy makers, probably it's an important aspect. So in this study, we will consider millimeter temperature, physiological equivalent temperature, and universal thermal comfort index (UTCI). And well, for developing a model that gonna work with safety simulations and also millimeter temperature that is for surface temperature. One of the most, I mean, for me, when I wanted to start a digital twin, the first aspect was that how can I manage the time? Because safety simulations take, like, it's really time taking, and I mean, it's out of my hand for softwares to choose, like, softwares are so limited in urban spaces. So it was my first challenge, and the second challenge was real-time weather data file because we cannot count on ETW files when we are talking about real-time simulations. So for generating real-time weather data file, uh, the method that we considered is to um, download the data file for short-term forecast from API, and then in JSON format, we use dry bulb temperature, relative humidity, wind speed, and sky cover, and we replaced dew point temperature, hourly, solar radiation, and direct and diffuse decompositions. So the modeling is done through Grasshopper, and we use, as we cannot use Energy Plus directly in Grasshopper, we use Honeybee. So after we reach this APW file that is like for short-term forecast, so it's more accurate in comparison to the real APW files. We have to manage the second challenge, that is CFD for the wind simulation for MRT. What we've done is that when you when we calculate CFD simulation through Honeybee, we are mostly facing OpenFOAM. OpenFOAM is a software for CFD. So it's so slow that it mostly disrupt any simulation. It takes more than 1 week if you want to like simulate a space like 600 to 700 square meter. It takes 1 week for a daily simulation. So I replaced the blue CFD through and in some aspects of CFD simulation to just speed it up, and then I use that for and then as you can see, it's like in this part I started for the EPW file, and I generated that new EPW file. And then we also had a 3D model, like all the trees with all the details of buildings. And then um, we had a surface temperature simulation that is also done in Honeybee graph software through the main engine, of course, is Energy Plus. And then we had that CFD simulation that we considered in Blue CFD and OpenFOAM for the meshes. And then we reached the last step, that is like combining all the like the flow of input and output together. One of the other aspect of um, making a digital twin in real time is that when we are using all different software, we should be so careful about the flow of input and output, because sometimes um, um, the output and the input are not in the same format uh, that make it like one software calculates, for example, the window speed based on like the mean radiant temperature, or thermal comfort based on temperature, mean radiant temperature, and then the other one calculates based on, I don't know, sun angle, and then when it wanted to match each other, it creates inaccuracy. So for the validation of our digital twin, we consider MARDI is the instrument that you can see in I use it in ASU campus for the validation in 5 points, and in 5 points in the campus. Then it includes like all the ascribing factors like shaded, exposed to sun, and the semi-shaded. And then these are the information of the 5 points that we validate the data. And these are the results of the validation. As it shows, the most accurate point actually is 3140, that the RMC is like 5.03, that it's a sun exposed like the point, and the worst one in fact was 3840, that RMC was like 9.4, that was a shaded area. So after validation, we started modeling in 3 different sites, like Bologna, Italy, Imola, Italy, and Tempe, the campus of Arizona State University. And these are the results. For the mean radiant temperature, it shows different context in the urban area, like the elevation is like low-rise or mid-rise or high-rise buildings, and also low cover, low canopy cover, and medium canopy cover, and high canopy cover. And the dash line also is air temperature that shows the differences. And if I wanted to compare them, is that in the context of Bologna and Imola in Italy, we can say that high-rise buildings are helping, the environment to cool down. But if we see a high-rise context in Tempe, in Arizona, we cannot make sure that it's the meridian temperature is really considerable, because whenever, even when it's the high-rise buildings ground, the the meridian temperature or UTCR shows extreme hot weather, extreme heat for the UTCR. So these are the results of universal thermal component index in the same points as meridian temperature, and the last one is PET that we just added to digital twin in a new site in Imola. So Imola is a historical city center in Italy, and again the campus. And these are the results, and the results were successful, as it could we could manage it real time. So if I want to compare it, it's like in Imola, because we have a compact context. Um, it showed a very comfortable uh, pedestrian, like for the pedestrians, for the temperature, but in Arizona, uh, it was almost red, as you can see, so it's like 50 degrees. So the real-time PET results from the proposed digital twin, we could show it on a resolution of 1 square meter uh, for a site like 700, 800 square meter, and with a laptop Intel Core i5, 60 gigabyte memory, and 8.5 gigahertz CPU. And the model shows that we minimize the miscalculation between different input and output, and the 3D model was managed with a detailed trees and building, and um, the last one is that I explained before about the input and output of the simulation. Thank you for your attention.
Thank you, Dr. Galami. Do we have time for one quick question? Yes. I'm going to take in your microphone.
I'm actually doing quite similar stuff, so I like it. But I'm wondering what the connection is between the measured data, how you're getting it into the grasshopper script, especially the wind, and connecting that to the CFD analysis.
We didn't use the measured data into the grasshopper. We downloaded the data from API. There is a short-term forecast website, so we use those data because it's for testing, so we cannot measure it. So we are doing real time, so we can like download the data like 24 hours, and then put it in the digital twin. So we cannot use the measured data for that.
And do you create like a new file?
Yes.
Thank you very much. Professor Lipping D will be presenting automated high-resolution LCZ mapping